So now we're going to focus on some functional groups. Remember, what we're just trying to do is remind you of the various functional groups that you learned in Organic 1. So we're going to look at several functional groups now that include the carbonyl group. So it's kind of like a subset of functional group. It's the C double bond O, where because of the electronegativity difference, that carbon gets the partial positive charge and the oxygen gets the partial negative charge, and then that sets up chemistry. Like, for example, the carbon now is like an electrophile, can behave as an electrophile. Okay, so let's look at some of these carbonyl functional groups, and in particular, we're going to look at aldehydes first. Okay, so one of the properties with aldehydes is that it can accept hydrogen bonds, but it cannot donate hydrogen bonds. You might be thinking, well, wait a minute, there's a carbon hydrogen right there. Can't that engage in hydrogen bonding? No, because remember that in order for a hydrogen to be donated in a hydrogen bond, it must be connected to a nitrogen, oxygen, or fluorine. Okay, so even though that hydrogen atom is a special part of this aldehyde functional group, that is not engaged in hydrogen bond donation. The lone pairs on the electron, or pardon me, the lone pairs of electrons on the oxygen, those can engage in hydrogen bond acceptance so that they can interact with a hydrogen on another molecule, but you cannot get involved in hydrogen bond donation. Also, this is one of those things where we just got to remind you that with skeletal structures, usually the hydrogens are not shown, they're implied. And so with an aldehyde, because it is an important atom, sometimes it's shown and sometimes it's not. So there you have examples of both those situations up here in this box. So for example, this one right here, the hydrogen is shown, but we didn't have to, as is illustrated right next to it. Because with a typical skeletal structure, hydrogens are not shown if they're connected to carbon. Hydrogens will be shown if they're connected to some other atom like oxygen or nitrogen. But the typical way to draw a skeletal structure will not show hydrogens attached to carbon. But sometimes, as I said, because it is an important atom in the aldehyde functional group, it's going to be written, but not every time. So just be aware of that. Be on the lookout for that. Okay. Also, be aware that not every time you have a hydrogen connected to a carbonyl group is it an aldehyde. If that's the important part, yes, it's an aldehyde. But you got to look at what's on the other side. So, for example, you can see right here, you have the oxygen and another R group, so that makes it an ester. So even though it's got the hydrogen connected to a carbonyl group on one side, it's got something that is more important on the other side. So we would call that an ester. We would not call that an aldehyde. So not every C double bond O bonded to hydrogen is an aldehyde. Just be aware when you're classifying functional groups, when you're looking for functional groups and classifying them. Okay. All right, another carbonyl containing functional group are ketones. And that is when you have two R groups connected to the carbonyl. Carbonyl has two sides, both sides occupied by R groups. And you can see those in the illustrations here. So again, hopefully this is all review. You're just trying to refresh your memory. So here's our carbonyl, and we've got an R group on both sides. Here's your carbonyl, you've got an R group on both sides. That's what a ketone looks like. Okay, it does have similar properties to aldehydes, but it is less reactive. So another carbonyl containing functional group that's important are carboxylic acids. So again, just kind of be aware that there's a couple ways to write these, in the condensed form in one line. Like if you're putting this in one line of text, like in a paragraph or something. Sometimes it's COOH, that means carboxylic acid. Sometimes it's CO2H. Because with the carboxylic acids, you have this hydrogen that's connected to an oxygen. It can do both. It can donate hydrogen bonds and accept hydrogen bonds. So that affects its properties, such as water solubility. Carboxylic acids have enhanced water solubility. Carboxylic acids are more stable than ketones. We're kind of going down the line of stability here, less stable to most stable. But you can make the carbon of the carbonyl electrophilic, particularly if you use it under acidic conditions, because the acid will act as a catalyst. So while moderately stable, the carbonyl carbon of carboxylic acid is electrophilic and can react with some nucleophiles, generally under acidic conditions. Okay, so here we go, some pictures of structures of carboxylic acid. So again, you can see that it's the C double bond O, and then there's also an OH group attached to that carbonyl carbon. Now, because its name is carboxylic acid, because we know the properties of that functional group, it, as the name implies, is acidic. And so if you are under basic conditions, what typically will happen is it rips off that hydrogen and creates what we call the carboxylate. Okay, so the term for when the carboxylic acid has been deprotonated is carboxylate. Okay, so under basic conditions, most nucleophiles will just remove that hydrogen, that proton from the OH, rather than add to the carbonyl. And then again, we know about pKa's, they're just a measure of the acid strength. The lower the pKa, the stronger the acid. So for carboxylic acid, that range is typically 4 to 5. Okay, so as I said, the carboxylate ion is what you form when you deprotonate it. It's the conjugate base. So carboxylate ions are the conjugate bases of carboxylic acids. They are highly water soluble due to their negative charge. And that makes that functional group a good nucleophile. So the negative oxygen of carboxylate ions is a good nucleophile. This oxygen right here is going to behave as a good nucleophile. So it's got these are really poorly drawn electrons, but those are lone pairs of electrons. And one of them is going to attack that carbon right there. Because again, remember this polar bond makes the bromine partial negatively charged, the carbon partial positive charge. So that's going to be our electrophile. And then this acetate then behaves as the nucleophile. Okay. And so, of course, that carbon can't have more than 4 bonds. So it's going to break this bond it has with the bromine. It's going to serve as our leaving group. It's a typical substitution reaction, probably an SN2 reaction. And then you form that bond. The bond that you form is when that oxygen forms a connection with that carbon. So one of the reasons why we start with carboxylic acids is because now we're going to look at different derivatives of carboxylic acid. They're like carboxylic acids, but they've been transformed in different ways. And so one of the ways that's common to transform a carboxylic acid is to turn it into something called an acid halide. And again, you can see some examples of that here in this box, where instead of an OH, it's been replaced with a halogen. Okay, so these are just some examples of acid halides. And one of the most important things to know about acid halides is that they are very reactive. Okay, so they are often a starting point in organic synthesis. If you want to, make something, a lot of times you'll start with an acid halide and then go from there. So acid halides are the most reactive. It's a common starting point to form other functional groups. A little bit less reactive, but still considered pretty reactive, are the acid anhydrides, or sometimes just called anhydrides. So they're not as reactive as acid chlorides or acid halides. I say, you'll catch me saying acid chlorides because that's the halogen that's usually used. It's usually an acid chloride, but it can be. There's nothing wrong with making it into an acid bromide or something like that. Okay. But it's not as reactive, but it's also a common starting point. So here's some examples of the anhydrides, and you'll see that the OH has been replaced with, the H, I should say, has been replaced with another carbonyl group attached to another R group. Okay, so acid halides are the most reactive, anhydrides are the next most reactive. So we're just going to keep going down the list. So the next most stable or less reactive than the anhydrides are the thioesters. Okay, so you can see from the picture there what a thioester is. It's like an ester because, remember, sulfur is 1 period below oxygen on the periodic table. But it's a thioester because it's sulfur instead of oxygen. That's the special terminology that's used. But the proper term for an amine that has been protonated is aminium. All right, so that's the first thing. Okay, well, once again, there are different types of amines. There's primary amines, secondary amines, tertiary amines, based on how many R groups are attached to that nitrogen. And as I said earlier, but I'll repeat it, okay, is that amines can both donate hydrogen bonds and accept hydrogen bonds, except for the tertiary amines, because the tertiary amines don't have any nitrogen-hydrogen connection. All right, so they can't donate hydrogen bonds. They can still accept hydrogen bonds, but they can't donate them. Okay. And as we said, the important thing about amines is that they behave as weak bases. So the nitrogen atom in amines behaves as a weak base. That lone pair on the nitrogen is the site that it works like a weak base. Okay, but that lone pair can also behave like a nucleophile. Okay, so it can attack a carbon. And we'll see that. So amines also behave as nucleophiles. Aminium ions then are the conjugate acid form of amines. Aminium ions are the conjugate acid form of amines. So they're positively charged, right? Because when it takes on, you can see that here, when it takes on that hydrogen, so it added that hydrogen right there, and then it has a formal charge of +1. Okay, so that means that that hydrogen is going to be slightly acidic. It can be removed. And actually the pKa is, it's not very low. The pKa is in the range of 9 to 11. So aminium ions are also weak acids. So amines are weak bases. Aminium ions are going to be weak acids. And so again, you can see in this box all the different types: primary, secondary, tertiary. And so you can see, like for example, on this one right here, you can see why this compound could not donate hydrogen bonds, because the nitrogen doesn't have any connection to hydrogen atoms. Okay, whereas like in this primary amine, there are nitrogen-hydrogen bonds, so it could donate hydrogen bonds. Okay, so just kind of moving on. So another way to incorporate nitrogen into organic compounds is through this functional group called nitro groups, NO2. Okay, so anytime an NO2 is on an organic compound, that's a nitro functional group. And we usually just talk about it as a substituent. It's usually not the most important thing in the compound. So it's treated more like a substituent than it is a functional group. We don't really get into the chemistry so much of nitro groups. We just focus on how it affects the chemistry of the molecule it's attached to. And that chemistry is, well, first of all, that notice it's got two charged atoms on it. So, look above in the box there. The nitrogen will always have the positive charge, but one of the oxygens is going to have a negative charge. Overall, it's neutral, but you got two atoms that are charged. That's kind of unique and interesting. But here's the thing that we want to know about nitro groups is that they are super electron withdrawing. Because of that formal positive charge on the nitrogen, it really draws out electron density because positive attracts negative, right? But also because of resonance forms. You could draw resonance forms most likely that will formally pull electron density into that functional group, okay, forming a double bond with the nitrogen. All right, but that's the big thing, is we consider it to be an electron withdrawing group, and a very effective electron withdrawing group. That is nitriles. So the key thing there is it's a carbon-nitrogen triple bond. You can see some examples there. So once again, this can serve as a hydrogen bond acceptor, but not a hydrogen bond donor. In this case, it's kind of a duh, because there's no hydrogens in that functional group, 0. Okay, also, just like with alkynes, the atoms involved are sp hybridized. So the carbon and nitrogen are sp hybridized. And so that means that we have a geometry of a linear geometry, a bond angle of 180 degrees. And again, nitrogen's electronegative, so it creates a partial positive charge on the carbon. It's going to behave like an electrophile, partial positive, partial negative. And remember that nitrogen also has a lone pair on it. Keep going. So another functional group that has nitrogen in it are the imines. And for now, again, we're not going to look at the reactions. Don't care so much about that right now. I just want you to recognize the connectivity of the atoms. Know it when you see it. But it is formed when you react an aldehyde or a ketone with a primary amine. And what you get is you get this carbon with a double bond to a nitrogen. So it's kind of like a carbonyl, but the carbon has a double bond to a nitrogen instead of an oxygen. And since nitrogen likes to form 3 bonds, then there's going to be another R group present connected to the nitrogen. So there's some just examples of imines. So again, just notice in each one of these cases, there's the carbon double bond nitrogen, carbon double bond nitrogen. Okay, and closely related because it's formed in a similar reaction, but it's got a unique, structure, template structure. We call them amines, but that's really, a contraction of 2 words, alkenes and amines, because you see both right together. So you have an alkene functional group right next to an amine functional group, and so we push those words together and call them enamines. Okay, now this happens whenever you have an aldehyde or a ketone reacting with a secondary amine. So just be able to spot the structure. So again, here's our alkene, that carbon with a double bond to another carbon. And then attached to it is also an amine functional group. So we got the ene, we got the amine. So if you look at these examples here, you got the ene, you got the amine, you got the double bond, carbon-carbon double bond, and also on one of those carbons, you have an amine functional group, so enamine. Whenever you start with a carbonyl containing functional group like aldehyde or ketone, and then you react it with alcohols. So not, the previous two functional groups we looked at, amines and enamines, we had a carbonyl reacting with an amine. Well, now we're going to look at some functional groups that form when you react that carbonyl with alcohols. Okay? You can form what are called acetals or ketals, and that depends on what you start with. If you start with an aldehyde and it reacts with alcohols, you form an acetal. If you start with a ketone and you react with alcohols, then you get a ketal. So aldehydes form acetals, ketones form ketals. So it's formed by the condensation of an aldehyde or ketone with two alcohols plus an anhydrous acid catalyst. So this one you do have to catalyze. But again, and I know we went over these reactions in Organic 1. We will go over them again later when we start talking about that chemistry some more. But again, today, I just want you to recognize the functional group when you see it. So, for example, here is an example of an acetal. You know it's an acetal because the carbon in the middle is attached to a hydrogen, but then you reacted it with two alcohols. So that's where those two alcohols reacted with the carbonyl group. So the carbon is connected to it forms two ether groups. So there's like an ether functional group there, there's an ether functional group there, and then it's still connected to the hydrogen. So that's an acetal. Now, if you go over here to where the ketal is, so remember we started with a ketone, so that's those R's right there, the R and that R at the bottom. Those are like the original R groups that were on the ketone, and they reacted it with two equivalents of alcohol, and so you form those two alcohol or those two ether groups. So that carbon that was part of the carbonyl forms two ether functional groups. That's called the ketal. All right, so now we want to contrast that with things called hemiacetals or hemiketals. And so what that means is just it's halfway. That's what that prefix hemi or hemi typically means. Okay, you've taken the reaction halfway. And so the characteristic thing with those is that yes, you form the ether functional group, that carbon connected to oxygen, connected to another R group. But then on the other side, it's just an alcohol. It stays as an OH. Okay, and this one is a hemiacetal or hemiacetal because that original carbon that was part of the carbonyl still has a hydrogen on it. So that hydrogen tells you it's a hemiacetal. Okay, compare the acetal with the hemiacetal, you'll see that the difference is that instead of two ether functional groups, you only have one ether functional group and one alcohol functional group. Same thing with the ketals. So you start with a ketone, and with a ketal, you have the original two R groups on the ketone and then two ether functional groups. But with a hemiketal or hemiketal, you form the one ether functional group, but then on the other side, it's just an alcohol functional group. So we've taken the reaction halfway. So it's the intermediate on the way to the acetal/ketal. It is the product reaction with one equivalent of alcohol. And if there's a cyclic form, then it's stable. That's only that's only possible with the ketals, by the way. But anyway, again, we're not worried about that today. Today we're focused on just picking out these functional groups when they're present. Okay, so now we get a chance to do that. Okay, so we'll use this matching question to do that. Okay. Now, some of these possible answers won't be used. So let's look at this one right here. So the one on the left here, we see that there's a nitrogen and it's got three R groups attached to it. There's one there, there's one there, there's one there. And so you might be tempted to think, oh, well, that's a tertiary amine. And that's not wrong, but also notice that part of one of those R groups is this alkene functional group. So we've got the ene and we've got the amine. So that's the best answer for this one is enamine.